Here's a script for a 9 to 12 minute educational YouTube video on reducer engineering. Cut your AI pipeline cost by 86% with one function. Hook, midnight to 0:30. Let's start with the numbers. We've got a Sonnet synthesis model that's being fed the output of 40 parallel Haiku workers. Without any optimization, this process costs $1.38 and takes 51 seconds to complete. But with a single Python function, which we'll dive into later, we can reduce the cost to 19 cents and the processing time to just 11 seconds. That's an 86% reduction in cost and a 78% reduction in processing time, all with zero changes to the model itself. The invisible problem, 0:30 to 2:30. So, what's going on here? When we run 40 parallel Haiku workers, we might expect to get 40 clean findings, but what we actually get are 40 small documents, each with its own preamble, formatting, and citation style. This is not what our synthesis model is designed to handle. In fact, research has shown that model accuracy follows a U-shape in long contexts, meaning it's strong at the start and end but significantly worse in the middle. By dumping 40 unordered findings into the model, we're putting most of them in exactly the worst spot. The real problem here is that we've built a research pipeline, but we're shipping a data cleaning job to the expensive model. The reducer function, 2:30 to 5 o'clock. So, how do we fix this? We introduce a reducer function that takes the output of our Haiku workers and prepares it for the synthesis model. Let's break it down line by line. We start with a finding data class that includes claim, evidence, source, confidence, and timestamp. All of these fields matter, and we'll see why in a minute. Our reduce_findings function performs three operations in order. First, we filter out malformed entries that are missing a claim, evidence, or source. This is not the model's job. We can do this with exact, free code that's never optimistic. Next, we group our findings by normalized claim, which means we collapse different phrasings of the same claim into one group. This is where the normalize function comes in, and we'll talk about the risks of false merges later. Finally, we keep the highest confidence finding per group and annotate it with corroboration information, like confirmed by 2 other workers. This is a signal that our synthesis model should see, not something it should rediscover by reading 40 documents back to back. We sort our findings by confidence in descending order, which beats chronological order because it prioritizes the most important information. The numbers explained, 5 to 7 o'clock. So, what do the numbers look like? We're going from 41,200 tokens to 5,300 tokens, which is an 87% reduction. This is why our cost drops from $1.38 to 19 cents. Our synthesis model is built on what it reads, and reading 87% less means we're saving most of the cost. The processing time also drops from 51 seconds to 11 seconds, because longer input means more time attending before producing the first token of the answer. But here's the best part: by grouping our findings, we surface 23 contradictions that were previously buried. This is because 2 workers on the same claim with different confidence levels creates a visible conflict, and 2 workers with contradictory facts are flagged, not silently averaged. The 4 guards, 7 to 8:30. We've also implemented 4 guards to ensure our reducer function is working correctly. First, if a finding is missing a claim, evidence, or source, it's dropped before grouping and logged, so we can see what's going on. Second, if 2 findings in the same group disagree, they're flagged as a contradiction and sent to the synthesis model explicitly. Third, if a group has only 1 member, it passes through unchanged, so we're not boosting false confidence. Finally, if the input is empty, the synthesis step is skipped entirely, so we're not running the model on nothing. Each of these guards catches something that used to depend on the Sonnet model noticing on its own. The playbook, 8:30 to 9:30. So, what's the takeaway? If you've got multiple workers feeding a final model, put a reducer between them. Deduping, filtering, and grouping are code problems, not model problems. Reasoning about what's left is the model's job. Measure your raw input size before you optimize anything else, and treat worker agreement and disagreement as data to surface, not noise to hide. Honest limitation, 9:30 to 10 o'clock. One limitation of our approach is the risk of false merges, where different claims are collapsed into the same group. We need to stress test our normalize function before trusting it at scale. Call to action, 10 to 11 o'clock. So, what's your current synthesis input size? Drop it in the comments below, and let's talk about how you can apply these principles to your own pipeline. By introducing a reducer function and optimizing your input size, you can cut your AI pipeline cost.